at this point now we're having to generate our own hints, and the way we generate our own hints, given a complex polynomial, is one of the ways is the rational root theorem, and then Descartes' rule of signs. And if we use upper-lower bounds, then we'll talk about that too in just a minute. Okay, so the rational root theorem. If you have a polynomial function with integer coefficients, it will have possible rational roots. Now, by the way, what's a rational? Rational is anything that can be written as a fraction. Okay, anything that can be written as a fraction. So it will have possible rational roots in the form of plus and minus p over q, where p is a factor of the constant for the polynomial. If you think back to the general form of polynomials, that's the a sub 0. And q is a factor of the leading coefficient, which in that general polynomial is the a sub n term. So I have an example here all ready to go. The rational root theorem maybe sounds more confusing than it actually is. First off, which one is the p? Well, the p is the constant here. Oh, by the way, what if there is no constant? What if there's a GCF of x or x squared or something like that? Well, factor out the GCF first, factor out the GCF of x squared first, and then the rest of it you can deal with using the rational root theorem. Okay, so the p is the constant, the one that doesn't have any x's, or it has x to the 0. So p is 6. It doesn't really matter whether it's positive 6 or negative 6, because we're doing plus and minus p over q's for all the possible rational roots. Okay, anyway, p is 6, so what are all the factors of 6? 1, 2, 3, and 6. Q is the leading coefficient. In this case, it is a positive 2. But even if it was a negative 2, it doesn't really matter if it's positive or negative for the p over q because of the plus or minus stuff we'll be doing. So q is 2, and the factors of 2 are 1 and 2. So if we were to just list the possible rational roots for this polynomial, possible rational roots, rational zeros, we would have p over q. We've got plus and minus. Now, do this orderly, and my suggestion is do all the p factors over the 1 first. So, and this is notes, so we're gonna do a little bit longer. So plus and minus 1 over 1, plus and minus 2 over 1, plus and minus 3 over 1, and plus and minus 6 over 1. Now, of course, when they're over 1, it's really just the whole number. So this is probably the last time we'll actually write it as something over 1. Normally, you're probably just going to say plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. Okay, the next ones, now we do all of them over 2. So we've got plus and minus 1 over 2, plus and minus 2 over 2. Now, wait a minute. 2 over 2. Isn't that really 1? So now it's notes. We're just going to go ahead and list it out. Let's list all of them out here. So plus and minus 3 over 2, plus and minus 6 over 2. Now, normally, if you see that you've got a repeat, you don't have to list it again. So 2 over 2, that's a repeat. 6 over 2, that's a repeat. You don't have to list them again because we already listed them once. So out of all the possible rational numbers in the world, which there's infinite number of them, the only ones that could possibly work in this polynomial are plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6, plus and minus 1/2, plus and minus 3/2. And so if they're just asking for the possible rational roots, you'd just list those and then you're done. And there could be a question on the test like that. And you just list those and that one is done. Then you move on. Okay, moving on. Descartes' rule of signs. This is for polynomial functions with real coefficients. Now we just need to go ahead and write it down. It looks a lot more complicated than it actually is. I'll do an example with you, and you'll see it's actually not that bad. But the number of positive real roots is equal to the number of sign changes for the function. Or you go down by 2's until you reach 1 or 0. The number of negative real roots is equal to the number of sign changes for f of negative x. So you're inputting a negative x. Or you go down by 2's until you reach 1 or 0. Finally, the number of imaginary roots for the polynomial function. We really haven't been dealing with imaginary roots yet, but we will start dealing with them now. The number of imaginary roots can be determined by the degree of the function and analysis of the possible number of positive and negative real roots. Much like the rational root theorem, if there is a GCF of x or x squared or something like that, make sure you factor out the GCF of x or x squared first. Obviously, those type of roots where there's a GCF of x is actually 0, so it's possible to have roots that are neither positive nor negative, and they're not imaginary either if they're actually 0. So pull out GCF of x if that's the case first, and then deal with the rest of it this way. Okay, let's do an example problem with it. So let's say we have y equals, well, let's just look at the one that we had up above. So 2x to the 5th minus 4x to the 3rd plus 3x squared minus 7x plus 6. Okay. Now, if we're going to check the positives, we're looking at the sign changes. Now, if we're going to look at the sign changes, let's write down what the signs are first. So we have positive, negative, positive, negative, positive. And then if we count the sign changes, now you only count a change. So just because there's a plus there, don't start counting until it actually changes. So positive to negative is 1, negative to positive is 2, positive to negative is 3, and negative to positive is 4. So there are 4 positive real roots. Or, go down by 2's. So, or 2. Have I reached 1 or 0 yet? No, so keep going down by 2's. So 4, 2, or 0 positive real roots. Those are the possibilities for this one. Okay, next we're going to check the negative. And when we're doing the negative, we're inputting a negative x. Okay, now, think order of operations. You have to do the exponent before you multiply by the coefficient. So if I input a negative x to the 5th power is negative, times positive 2 is negative. If I do negative x to the 3rd, I get negative, times negative 4 is positive. If I do negative x to the 2nd, I get positive, times positive 3 is positive. If I do negative x times negative 7, I get positive. And plus 6, there's no place to plug in an x, so the sign does not change there. Now, you only count the sign changes. Negative to positive is 1 sign change, and so there is exactly 1 real negative root. One real negative root. Okay, now that leaves us the imaginary. Okay, now imaginary. It says determined by the degree of the function. So first off, what's the degree of the function? The degree is 5, which means how many roots do we have? We have 5. There are 5 roots. Okay. Okay, so we know that there's going to be a total of 5 roots. What if 4 of the roots are positive and 1 root is negative? Well, in that case, there would be 0 imaginary roots. Okay, but what if it wasn't 4 positives? What if it was 2 positives and 1 real root? Well, then you'd have 2 more roots that you would need, and they would be imaginary. Okay, well, what if it wasn't 4 or 2 positives? What if it was 0 positive real roots and 1 real root? Then that means we would need 4 imaginary roots. And there's our possibility for the imaginaries. By the way, notice that it's even numbers because imaginaries come in pairs. Now, sometimes we might even ask you just what are the possible positive or negative or imaginary roots? And so that could be a test question too. But we need to put all of this together. And so the next problem we're going to do just that. Okay, the first example where we put all of this together is example A. You'll see it when you get the worksheet 7B, if you don't already have the worksheet. Anyway, we're supposed to find all the roots, state their multiplicity, factor completely. Now, don't forget, factor completely always means factor completely over the integers and sketch. Okay, now since we're sketching ultimately, it doesn't hurt to go ahead and take a quick look. You can see that it's going to be a high to low polynomial. You can see that the y-intercept is going to be 20. We already know that. But we can't factor this the way it looks except by division. And we weren't given any hints. We have to generate our own hints. And so here we go. The possible rational roots, the P over Q's. So P over Q, and again, remember it's plus or minus already anyway. So the P is 20. So 1, 2, 4, 5, 10, and 20. The Q is -1, but again, because of the plus or minus, you don't really need to really worry about if it's plus or minus for the P and Q. We're going to be doing plus or minus. So Q is 1, and that's nice because, so really all of our possible P over Q's are going to be plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 5, plus and minus 10, plus and minus 20. So there's the possible rational roots. Now, when we try these, my suggestion is to start with the smaller numbers and then work your way to the bigger numbers. Don't start with the big numbers and work your way to small numbers. Okay. Secondly, checking Descartes. So if we're going to do the positives, right now the signs are negative, positive, negative, negative, positive. And so the sign changes. 1, 2, 3 sign changes. And so we have 3 or 1. I've reached 1, so stop. 3 or 1 positive real roots. And then the negatives. So we're inputting a negative x, so negative to the 5th times -1, positive. Negative cubed times positive, negative. Negative squared times negative, negative. Negative x times -21, positive, and positive. So we have 1, two sign changes. Therefore, we have 2 or 0 negative real roots. Checking the imaginaries. Since we know there's a total of 5 roots, if we have 3 positives and 2 negatives, there are 0 imaginaries. If we have 1 positive and 2 negatives, we have 2 imaginaries. If we have 3 positives and 0 negatives, we have 2 imaginaries. I don't need to write 2 again. If you have 1 positive and 0 negatives, you would have 4 imaginaries. So the possible imaginaries is 0, 2, or 4. Okay, now at this point, we've generated our hints. It just comes down to the fact that we have to try some things now. And we want to do synthetic division because then it actually reduces the polynomial. We need to reduce it because we don't want to just kind of randomly find roots. We want to reduce it as we're going along so that eventually we're going to get it down to a second degree polynomial, and at that point, whatever's left, we should be able to handle without guessing and checking anymore. Okay, so looking at the possibilities, we have 3 or 1 positives, 2 or 0 negatives. Probably, and the P over Q's, I'd probably just start with positive 1. Now, as we're doing this, you need to have some patience. You probably need to use a pencil as you're doing it. So I'm doing positive 1 here. Always double check to make sure, did it skip any powers of x? Because if it skips any powers of x and we're doing synthetic, remember you must put a placeholder. So notice it skipped the power of 4. If you're not noticing that sort of thing, you know, you might have a problem and maybe there was a power that was skipped and you tried all your P over Q's and not one of them worked, and you might get upset with us and you might say, this problem doesn't work. And we say, well, look, the power got skipped and you didn't put a placeholder there. So don't get upset at us. Get upset at yourself if you're not paying attention to that sort of thing. So negative 1, 0, 22, negative 20, negative 21, and 20. Okay, it's all set up. Like I said, really, you want to do this either on some scratch paper off to the side or until you know if it works or not, or do it in pencil so that you can erase. Okay, so actually, since I need some scratch, I'm gonna do scratch paper off to the side, just so I will know if it works or not, because I'm using pen. So 1, negative 1, 0, 22, negative 20, negative 21, 20. Okay, so here we go. Negative 1, negative 1, negative 1, negative 1, 21, 21, 1, 1, negative 20, negative 20, and 0. Yay! Okay, so 1 worked. So I'm going to fill that in on my real piece of paper. Okay, so I had negative 1, negative 1. Now, once you find one that works, do that dividing line, separate the remainder. You do not want to go into the remainder stuff. We've reduced the equation. We've reduced the equation from a 5th degree down to a 4th degree, and you want to keep on working with the reduced equation. Okay, so we found 1. What are we going to try next? Well, I have 3 or 1 positives, and 1 just worked. Could it work again? It might. Maybe the multiplicity is more than 1. So I think I'm just going to try 1 again. Okay, and so negative 1, negative 1, negative 2, negative 2, 19, 19, 20, 20, 0. Yay, it 1 worked again. Okay, so 1 worked again, and I have reduced my polynomial from 5th degree to 4th degree to 3rd degree. Now, according to what we figured out, there are 3 positive real roots, or 1, but it's got to be 3 because I've already got 2 positive real roots. So it must be 3. Could 1 work again? 1 could work again. So we could go ahead and try 1 more time. Now I've already done this problem ahead of time, so I'm going to do it in pencil right now just to kind of look and see. And so 1 in the box, and -1, -1, -3, -3, 16. It's not going to work, is it? Because we're going to get 36. Okay, so I am going to erase, and so instead of +1, what am I going to try? Probably I would go ahead and try -1 at this point. So -1, first one comes down, -1. So now I get 1, -1, 1, 20, -20, 0, yay. Okay, we've gone from 5th degree to 4th degree to 3rd degree. We're now down to 2nd degree. At this point, stop guessing and checking. Just because we've generated all the P over Q's, once you get down to the 2nd degree, it might not even be a P over Q. This might not factor. But then again, it might, so let's check it out. So we've got -x² minus x plus 20. Okay, well, let's factor out the GCF of -1. And we look and we, oh yeah, that factors, doesn't it? Okay, so that factors as x plus 5 and x minus 4. Now let's go ahead and write it out in completely factored form. So y is equal to, now don't forget our GCF of -1, so negative, and I think I'll start down here, the x plus 5, the x minus 4. Okay, now what are the other factors? Well, what's the -1 in the box represent? Represents x plus 1, x minus a -1. What do the ones in the boxes represent? They represent x minus 1, and there's 2 of them, so x minus 1, there's 2 of those, so x minus 1 quantity squared. Okay, now, if we multiplied this all the way out, isn't that negative x to the 5th plus a bunch of stuff? Yeah, we can see that that would be negative x to the 5th, and that's what we started with. We started with y equals negative x to the 5th, so here is our completely factored form. Our roots, our zeros, are -5, 4, -1, and +1. Now, shouldn't probably list plus and -1 because the +1 has multiplicity of 2. Okay, so there are all the roots. And we need to go ahead and sketch this now. Okay, so quickly sketch. We've got -5, +4, -1, and +1. Now the only one that bounces is at +1. Remember, we already looked this over and we determined it was a high to low, so high to low, and it bounces at the positive one, but it goes through at all the others. So starts high, goes through, bounces, and goes through, ending low. Okay, so label all the intercepts. We've got -5, we've got -1, got +1, I've got +4, and don't forget about our y-intercept. Our y-intercept, we figured that out earlier. If we plugged in 0 for all the x's, we get 20. Okay, and so that problem is done. Okay, I know we just finished that last problem, but let's talk about upper and lower bounds real quickly. That was in the title, and I haven't really talked about them yet, so now is a good time to talk about it. First off, bound is short for boundary when we're talking about upper and lower bound. So when we're saying upper bound, it's the upper boundary. When it's lower bound, it's the lower boundary. Okay, so if something is an upper bound means there are no roots, no zeros to the right of the upper bound. So, for example, 4 is an upper bound for our previous problem. Now, for that matter, 5 is also an upper bound, or 6 or 7 or whatever, but 4 would be the most useful one. Now, why are we talking about upper bound, lower bound? Well, we might be giving you some hints, and so if at the beginning of the problem, if I had told you that 4 was an upper bound, I'm trying to, as long as you understand it, I'm trying to make your life a little bit easier. So, for example, if we looked at all of our P over Qs, and if I told you that +4 was an upper bound, then that means you know that 5 wouldn't work, 10 wouldn't work, 20 wouldn't work. Anything past 4 would not work. Now, in a similar way, lower bound means lower boundary. So a lower bound has no roots. A lower bound has no roots to the left of it. So, for example, the previous problem, if I could say that -5 is a lower bound of this function, because there are no roots, no zeros to the left of -5. Okay, now technically -6 is also a lower bound, and -7 and so on. -5 would be the most helpful lower bound. Okay, so now if we talk about lower bound, upper bound, we're trying to make life a little bit easier for you. We're trying to narrow your search parameters. Okay, it would be good for us to do another problem here, but rather than just doing some stray example, I thought I would go ahead and do one of the problems from the actual assignment. We have 8 problems that we're doing. Now, the directions, I think they said just 1 through 7, but you're actually doing 8 problems. And these are due tomorrow. I thought maybe we would do problem number 4. Maybe we'll even do one other problem, but problem number 4, we can do that one together. Same directions that we just did. So problem number 4, we have y equals 3x to the 4th minus 4x to the 3rd minus 52x squared plus 64x plus 64. Okay, so looking ahead, it's going to be a high to high, and the y-intercept will be positive 64. Our P over Q's, P is 64, and just think about all those possible roots. And Q is 3, so 1 and 3 are the factors. So possible P over Q's, plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8, plus and minus 16, plus and minus 32, plus and minus 64. Those are all the ones that are just over 1. We also have all of those over 3, so plus and minus 1/3, plus and minus 2/3, plus and minus so on. I don't really feel like listing them all out, and you probably don't either. Okay, Descartes' rule of signs, checking for positives. The signs currently are positive, negative, negative, positive, positive. So that is 1, 2, so 2 or 0. The negatives, if we plugged in negative x for each one of these and worked out the signs, we would get positive, positive, negative, negative, positive. And so we get 2 or 0 from that as well. Okay, which means imaginaries. If we have 2 and 2, we would have 0. If we have 2 and 0 or 0 and 2, we would get 2 imaginaries. And if we had 0 and 0, we would get 4 imaginaries. Okay, so now at this point, we just have to try some things. Let's set it up. 3, negative 4. Oh, double check. Did it skip any powers? No. So 3, negative 4, negative 52, 64, 64. Okay, and I'm just going to try positive 1 to begin with. Okay, so here we go. 3. The first one coming down will be 3. I'll put that in pen, because that's not going to change. So 3, negative 1, negative 1, negative 53, negative 53, 11. No, 1's not working, is it? So I'm going to try negative 1. This would be negative 3. So let's see, we get negative 7, 7, negative 45, 45, 1, negative 1's not working. Okay, so I'm going to mark off the fact that we've done plus and minus 1. They're not working. Okay, so what am I going to try now? I'll probably try positive 2 next. Okay, so 2, so 3, 6, 2, 4, negative 48, negative 96, negative 32, negative 64, 0, yay! Okay, that one worked. I'm going to darken that in with pen. And do the little squiggle thing to separate the remainder. Box. Okay, now I have 1 positives, which means I'm going to have total of 2 positive, according to Descartes, because it's either 2 or 0. So if I have 1 positive, I know I have another one. I'll probably go ahead and try 2 again. Okay, so first one comes down as a 3. So let's see, 6, 8, 16, negative 30. No, 2 is not working again. Let's try negative 2. So let's see, that'd be negative 6. Negative 4, 8, negative 4. No, negative 2 doesn't work either. Okay, so we've done plus and minus 2 now. Okay, so what will I try? I'll try 4 next. So let's see, we get 12, 14, 28, 56, 8, ooh, 32, 0, yay! Okay, so I'm going to darken that in with my pen. Okay, now we've gone from 4th degree to 3rd degree to 2nd degree, whatever's left. Now, it might not even factor. Whatever's left, we need to be able to deal with. This is 3x squared plus 14x plus 8. That might factor. 3x, x, maybe 4 here and 2 there, both plus. 12x, 2x, yeah. Okay, so it did factor. It doesn't always factor. Let's write the factored form. So y equals, I'll start here, 3x plus 2, x plus 4. What about the 4 in the box? That would be x minus 4. What about the 2? That would be x minus 2. Okay, now, if we multiplied that all the way out, not that we want to multiply it all the way out, don't we get positive 3x to the 4th? And that's what we're supposed to have. So there is the factored form. The roots, well, the 3x plus 2, that would give me negative 2/3. And then negative 4 and positive 4. You could put plus and minus 4 since they're both multiplicity 1. And also positive 2. So total of 4 roots. We're supposed to have a total of 4 roots. By the way, just incidentally, notice we have 2 negative roots and 2 positive roots, much as we predicted. Okay, moving on. By the way, sketching. Okay, remember it started high and it ends high, and all these have multiplicity 1, so they all go through. So it starts high, goes through, goes through, goes through, goes through, ends high, label all the intercepts. Don't forget the y-intercept. The y-intercept is 64, and that's good. Okay, let's do one more together, and maybe let's go ahead and do problem number 7. Okay, so problem number 7. I've got it all written out already. You can go ahead and write it out. Let's generate our possible rational roots. So the P over Q's, so plus and minus. Okay, so factors of 12 over factors of 1. So really it's just the factors of 12. So plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, plus and minus 12. Those are all over 1. The possible positives, let's see, we have negative, negative, positive, 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 positive. So that is 1 sign change. The possible negatives, we would have positive, negative, negative, positive, negative, positive. So 1, 2, 3, 4. So 4 or 2 or 0 negative real roots. Okay, which means our imaginary possibilities, just for practice because this is going to come up, if we have 1 positive and 4 negatives, and by the way, the degree is 5, so 1 positive and 4 negatives, that would be all the roots, so 0 imaginaries. But if it's 1 positive and 2 negatives, then 2 imaginaries. If it's 1 positive and 0 negatives, it would be 4. Now, so far, it's the imaginaries has always been 0, 2, or 4. It's not always 0, 2, or 4. But it is always even numbers because imaginaries come in pairs. Okay, so we got to try something. Let's set it up. Double check, make sure, did it skip any powers? No. Don't forget to check that, really. Because if it skips a power, you need to make sure you put a placeholder of 0. So -1, -5, 7, 37, 38, and 12. And I'm just going to try +1. Okay, so -1, -6, -6, 1, 1, 38, 38, 76. No, 1's not working. And try -1. Okay, so -1, we would get 1, -4, 4, 11, -11, 26, -20, no. Wait, what's 38 minus 26? 12, -12, 0. Sorry, I spoke too soon. So -1 does work. I'm going to darken it in. And I'm going to do my little dividing squiggle there between the remainder and the rest of it. Okay, so we have reduced it from a 5th degree down to a 4th degree. Now, that's 1 negative, which means we got at least 2 negatives. So, could -1 work again? Yeah, it could work again. I think I'm going to try -1 again. So, let's see. -1, 1, -3, 3, 14, -14, 12, -12, and 0. Yay! Okay, it worked again. I'm going to darken it in. Another squiggle between my reduced polynomial and my remainder. And, okay, now, could -1 work again? Yeah, it might. I think I'll go ahead and try it. So -1, 1, -2, 2. No, because that's going to be 6. No, that's not working this time. So I have done plus and -1, and they neither plus or -1 will work anymore. I could go ahead and try a +2 or a -2. I'd probably go ahead and try a +2. So let's see, -2, -5, -10, 4. No, because I'd get 8, and that's not going to work. Okay, so let's try -2. Could be +2 then, and that'd be -1, -1, 2, No, that's not working anyway either, because that's 16 and times negative, no, so that's not working. Okay, so plus and minus 2 is done. Let's try 3. Okay, so I'll try 3. I get -3, -6, -18, -4. -12, 0, yay. Okay, darken that in. It's +3. Little squiggle there. Okay, now I've gone from 5th degree to 4th degree to 3rd degree to 2nd degree. Whatever's left, we need to be able to deal with it. So -x² minus 6x minus 4. Well, first off, I notice there's a GCF of -1. And I look to see, does it factor? No, it doesn't factor. But there are 2 roots in there, and we need to get the roots even if it doesn't factor. But on the other hand, the directions are to factor completely over the integer. So at this point, we can go ahead and factor completely over the integer. So let's do that. So our polynomial is y equals, don't forget the GCF of -1, negative. I'm going to list this polynomial right here. It doesn't factor over the integer, so I'm going to go ahead and write that one down right now. X² plus 6x plus 4. Okay, now we have the 3 in the box, so that's x minus 3. We have the -1 in the box twice, so that's x plus 1 quantity squared. If we multiply that out, do we get the -x to the 5th like we're supposed to? Yes. So that's the completely factored over the integers, since the x² plus 6x plus 4 does not factor over the integers. Now, the roots. There are 2 roots in there. How do I know there's 2 roots? It's a 2nd degree. There's 2 roots. So either you can use quadratic formula, or you can solve by completing the square. Since it's a +1 in front of the squared term and it's an even number, I think completing the square would be very nice. So x² plus 6x plus 4 equals 0. Move the 4 to the other side. It's -4. And I like doing plus blanks. So half of 6 is 3, squared is 9. And I need a 9 on the other side to keep things in balance. And so that's x plus 3 quantity squared equals 5. And square root, and we have absolute value of x plus 3 over here, but we're okay as long as remember to do the plus or minus as you're solving. Okay, so we've got x plus 3 equals plus or minus √5, and finishing solving for x, we have x equals -3 plus or minus √5. So as far as listing the roots are, well, we just got those 2 right there, -3 plus and minus √5. We also had, here are the roots that we had over here that worked as well, the 3 and the -1 multiplicity 2. So 3 and -1 multiplicity 2. Okay, there are all the roots. Now, how many of those are x-intercepts? How many distinct x-intercepts? We have 5 roots. Well, -1 is only counted once if we're counting x-intercepts. 3 is counted once, and then -3 plus √5 is an x-intercept, and -3 minus √5 is an x-intercept. There's 4 x-intercepts. Okay, so sketching the graph of this. Okay, so we've got 3 out to the right, I've got negative 1 to the left. Now, I need to know what negative 3 plus and minus root 5 is. Of course, root 5, it's a little bit more than 2. So negative 3 plus, like 2.2. Well, negative 3 plus 2.2, that's a little bit to the right of negative 1. We've also got the negative 1 right there, that's the root. And we've also got the 3. And then negative 3, negative 3 minus root 5, so negative 3 minus 2.2-ish. That's about negative 5.2. So negative 1, 2, 3, 4, 5, about negative 5.2. Now this was a high to low, if you remember. It bounces at the negative 1, so starts high, goes through. It bounces at the negative 1, but it doesn't get to go up very much because then it has to go through at the next root, and then it has to go through at the next root after that. Label all of our roots. We've got, this one is negative 3 minus root 5. Here is negative 1. I'm going to draw an arrow. That one right there is negative 3 minus root 5. This one is 3, and the y-intercept is 12. Okay, so you guys need to complete the rest of 1 through 8. We just did 4 and 7, so you've got 6 more problems to do between now and the next class.